So welcome to Math466, Advanced Applied Analysis. So I basically threw a bunch of words in the title to give myself maximum flexibility in terms of what we can do. This is a class which will really be influenced by what you want to study. So a lot of it is going to be working on projects. I've been talking with various people in industry as to what skills do they want students to get. What do they want them to master? A lot of it is being able to run a project, being able to present information, being able to find ways to visualize data so that other people can understand what you've done. So if you want, I am happy to adjust the grading system and essentially remove the midterm, and maybe even part of the final or all of the final, if you are really working well on a project and making progress with that and doing something of import. Okay, what I want to do today is go through the course mechanics. For those of you who've had a class with me, you will notice that these slides are extremely similar, and then talk a little bit about some of the applications that you can do with material like this. So in some sense, for those of you who took operations research, it will be somewhat similar to that in that the class will be somewhat schizophrenic, where you'll have the theoretical part and you'll have the applied part, and they will only be tangentially related to each other, because a lot of times you do not need to use the most advanced mathematics in the initial run to make progress. You know, a lot of times nothing has been applied. The people who are looking at these materials don't know math, they don't know stats. So anything you do is going to be progress. And so you already have enough. I see people wincing, but it's true. So don't worry about taking into account third order effects. They haven't even done first. You can even argue as to whether or not they've done zeroth. Okay? So just be careful. Now, the classes are being recorded, so what that means is I have to be a little bit careful. Anybody know about the MIT professor with the Affordable Care Act? He was caught at 5 different events talking about how we had to lie to the American public as to what was in the Affordable Care Act, because if we told them the truth, they never would vote for it. Well, as soon as he said that and the clips of that went out, all of a sudden he loses a lot of his consulting contracts. You've got to be very careful. In a standard class like complex analysis, I'm not really worried about what I say. Complex analysis is not a very controversial, heated discussion. I want to talk about applications of math in the real world. I'm on a regional school committee right now, and there's a lot of stuff going on there. And so if you want to know more, I'm happy to talk more about it off the record, and I will leave it at that. Okay, introduction and objectives. So obviously I want you to learn topics in advanced topics in analysis, okay? I want to emphasize the techniques. Most of you are not going to be using specific facts, but you'll be using mindset. You know, how do you frame a good problem? How do you ask the right questions? How do you go about gathering? The more math you've seen, the more extensive your toolkit is. And then when it's time to attack, hey, wait a minute, I saw this thing called linear programming. Maybe a linear program could help me resolve this problem. Is it recording? Just because it did not record last class. Okay, the numbers are going up. Excellent. Yeah. I want to prepare you for either grad school or industry. And so how many of you are seniors who are going to be doing job interviews? Okay, so I should have that somewhat later on. If you need to adjust any deadlines because you have a job interview, you have to prepare for a job interview, you have to travel for a job interview, you have to pick up Red Sox tickets for me, any conditions like that, just let me know, and I'm happy to adjust things accordingly. If you have a big extracurricular, anything like that, as long as you let me know at least a day in advance. If it's within 24 hours, the answer is no. But if you let me know at least a day in advance, usually I can work with you. There is one exception to when you're allowed to let me know less than a day in advance. It's the obvious one. Can you think of it? Big company calls you up and says, we'd like to see you. Are you free today? Are you free tomorrow? Your answer is yes. And then you send an email, Professor Miller, I'm really sorry, I have to leave right now. You know, something like that, obviously fine. But for the most part, know when your deadlines are going to be. Know when you're going to have the big commitments. Let me know in advance. There's going to be a lot of expertise you can gain from proofs and a lot from applications. I've done a lot of work over the years with a professor of accounting. And a lot of times the questions he asks leads to really good math quantities to investigate. And so the real world is a wonderful source, especially in the more applied sections of things to look at. All right. The other thing is to see applications of earlier courses. How many of you have taken a stats class? How many of you have not taken a stats class? Okay. I've taught stats, and I took it from the psychology department, but I'm not going to count that really as a stats class the way it was taught. And I don't mind saying that on the record. Basic stats is extremely important. If you have not taken basic stats and you have any desire to go into industry, I urge you to take a stats class before you graduate. Even if you are not going to go into industry, if you want to go to grad school, it's still worthwhile to know stats. A lot of the stuff you will be doing, you'll be gathering information, you want to analyze it. There's a great quote by the Nobel laureate Rutherford: if your experiment needs statistics, you did the wrong experiment. You're basically applying, your results should be so overwhelmingly convincing that you don't need to argue with somebody. Well, this is 100 years later. We have extremely small effects that we're often looking for, and we have massive amounts of data. You need to know statistics in the 21st century. Okay, so types of problems. So we have a lot of flexibility. This is a small class. This is a dream for a professor to teach a class like this. I feel like I'm in Div 1. Actually, no, this is probably still too many people for Div 1. But okay. So here are 3 things that I definitely want to do. I want to do Benford's law of digit bias. There's a lot of beautiful mathematics. There's wonderful applications of Fourier analysis. It also has incredible applications to the real world. It's the only time I've given a math talk where people told me in advance that they are carrying weapons. I was at the Boston headquarters of the IRS, and there were Secret Service agents there. And it was wonderful talking to them about how you can use Benford's law to detect tax fraud, or voter fraud, or various things like that. Random matrix theory is another wonderful topic. It turns out that if you choose matrices and put in entries at random, this describes a whole slew of systems, from things related to prime numbers to energy levels of heavy nuclei. So I want to talk a little bit about how you would prove results along these lines. The last is probability of the central limit theorem. I know several of you have taken probability with me in the past. The central limit theorem, as the name highly suggests, is extremely important. How would you prove something like this? What are the techniques you need? So we've sketched a proof that was mostly true in probability in previous years. The question is, can we make it fully rigorous? If you're taking complex analysis, the answer is yes. If you're taking just this class, I'm not sure if we can make it fully rigorous, but we can make it a little bit more so and highlight a little bit more what's going on, talk about other situations where maybe things aren't identically distributed, or just see some applications. And one of the big applications of this is actually to Benford's law. If there are other topics you want to see, please let me know. I am happy to discuss. Okay, so some of my experience. So I've done a lot of consulting work over the years. Some of you have done consulting work with me on medical. I've done some stuff with financial firms, policy, sabermetrics. Theoretically, I prefer number theory and probability, do a little bit in physics as well, but I've also done stuff in economics, marketing, geosciences, computer science. When you know mathematics, you can apply it to lots of different areas. And one of the nice things about this is you're going to be learning general techniques, and you can use these in a variety of settings. Okay. Thank you. It's okay. All right, so course mechanics. Okay, it looks like we're now drunk, so.
Yeah, way worse.
Okay, so technical issues. This is the problem. It takes a while to get things properly calibrated for each room. Do you want to adjust the legs, or?
No, it's decided to center you, and it can't be seen to slide.
Oh, okay.
No, that's better.
That's better. All right, so how's this? Is it?
Yeah, it's
Okay, I feel like I'm at the eye doctor, where they keep putting on different lenses. Better, worse, the same. Okay, so.
You can definitely stand up.
If it's working right now, I'll do the same, because this is the day I really need my steps. So right now I have class participation at 5%, homework 15, midterm at 40, final exam at 40. But as I said, if you're really interested and there's a project you're working on, I am happy to adjust these percentages so that you can devote a lot of time. I think you learn enormously when you are trying to apply mathematics and solve real-world problems. Prerequisites are real analysis. We have a new numbering for our courses this year. So this is a 400 level senior seminar, but it's a post 450. So that means it's supposed to be more intense than the pre-450s. Okay, just making sure everybody is understanding that. Somebody told me in the earlier class that it might be Williams 1793. I'm not sure which one of them works to send me the anonymous email. Someone changed the password a while ago, and I had to reset it, but I can't remember now which is the right one. And I thought I had checked, but somebody noticed that they were 2 different ways on 2 different sheets. So one of them should work. And this is a way if you want to send me feedback about how this class is going, or if you want to send me feedback about something else either on campus or in general that you just want to flag and have someone look at, this is a way for you to do so. Okay. Most of you have taken a class with me in the past, so you know I like to use old-fashioned looking web pages. I basically dump all the information on that. I don't use Glow. This way, when they send out emails saying we've just moved to Glow 2.4 and we will have a faculty training session, I can just hit delete. Okay. Prepare for class. Okay. So sometimes that means you will have to read a chapter. Is it off-centered now?
It's still good.
Close enough, exactly. All right. And then these are the advice from my brother. Party less than the person next to you. There's only 2 people who are in a row with someone next to them. So the rest of you should be extremely studious. You know, we have to just be careful with these men. You know what they're like. All right. Take advantage of office hours and mentoring. One of my favorite Williams students a couple of years ago was a math econ double major, went to Harvard, and he told me that there was an auction and the most bid upon item was an hour of a professor's time. And all the students in the class were bidding on this so that they could actually talk to their professor. Williams has a slightly different philosophy. Now, we're still trying to figure out exactly how to make things work in the new Bascom building where things have been rearranged. We can't have chairs outside our offices in my wing of the building because that's a fire hazard. So there's the seminar room, so you may have to wait in there, let me know that you're there, and I'll come and get you when I'm done with somebody. But strongly encourage you, talk to each other, talk to me, talk to the other faculty. Take advantage of the fact that the people who are here because we want to be talking with people. And then the last is learn how to manage your time. Time management skill is, I think it correlates with success better than ability. There are a lot of very talented people out there, but a lot of people don't finish what they said they will do, or they don't do it in a reasonable amount of time. If there's something that you can do quickly, do it quickly. Impress people by getting it done. Okay, I am happy to do practice interviews, especially for those of you who are applying for real jobs. I will make up the name of a company, or give you something, or you tell me what industry you're looking for. If you haven't gone through a job interview, do it either with me, do it with career services. Don't walk in for your first real interview at a company, okay? When people are applying for professorships, you often, if you can, arrange to have your first interview with a school you do not care about strongly. One of you, well, I'm pretty sure I have a good chance of getting a campus interview from this school, so I can afford to not shine as brightly there. Okay, so since this is a 400 level class, I want to just really dive into the subject. No first day, carefully treading, whatnot. This does not mean I'm going to throw an enormous amount of mathematics at you. I want to describe a real-world problem that Williamstown is actually facing right now. It affects you indirectly because it affects the school system, and having a good school system helps us attract good faculty. If we have a bad school system, that could negatively impact our ability to retain people. So right now, Williamstown and Lanesboro have 3 schools between them, 2 elementary schools and a high school. We have 4 school districts for 3 schools. Yes, we have 4 school committees for 3 schools. The 2 elementary schools are their own district. Then there is a super committee between the towns of Williamstown and Lanesboro for just the elementary schools. The high school is regionalized between the 2 towns. It's a high school, junior high school. And then the super committee above the 2 elementary schools coordinates things with the high school for certain shared services. This allows us to have 1 superintendent for the whole district, which saves money. But administratively, it's a nightmare where you have the top people, rather than working with the students, going to the same meeting 3 or 4 times. We are in the midst of discussing how to fully regionalize our 2 towns. There are a lot of reasons why you want to do this. A lot of them have already been done by forming these 4 regions that share services. So a lot of the financial savings have already happened, and most of the money has already been saved. We have a few more grants we can apply for now as a region. Massachusetts refunds transportation costs for a region at a higher rate than at individual towns. And so we'd be able to get maybe an extra $100,000 to $200,000 a year from the state if we bring the elementary schools in, which is not small change. The fear is, in Williamstown, a lot of people are afraid that Lanesboro will not let them spend the money they want and they will lose local control over their elementary school. Some people in Lanesboro are afraid that Williamstown will force them to spend more money than they want. And so it is extremely important for many people that we come up with a way to allow each town to control their elementary school. The state will not allow a sham marriage for a region. So we can't say we fully regionalize, but then have another committee or subcommittee that just deals with the elementary school, and the elementary school has a separate budget. It has to be a real marriage. And some of the biggest stumbling blocks is what's called Chapter 78. So right now, we get about $3.5 million a year from the state. To put things in perspective, the Lanesboro elementary school budget is about $2.7 million. The Williamstown elementary school budget is about $6 million. The high school is around $11 million. So on $20 million, $3.5 million is a significant amount. Right now, the state tells us how much money goes to Williamstown Elementary West, Lanesboro Elementary Less, and Mount Greylock, Mount G. If we were to fully regionalize, they will no longer tell us how much money goes to each place. They will just tell us, here is the lump sum that you now get as a region. And we need to figure out how to divide it. So one possibility is, of course, to just split it, 33, 33, 33, but that's not even close to what's going on historically. Historically, the high schools gets about 50%, Williamstown about 28%, Lanesboro about 22%. Williamstown Elementary is about twice the size of Lanesboro Elementary, but there's a lot of demographic factors that go into how the state calculates it. I've heard it has a huge number of variables, but they don't share the formula. So we need to figure out how to do this. So anybody want to say explicitly what's the goal and suggestions on how to accomplish it? You always want to identify the problem. Yes?
So the goal would be to achieve somewhat of an equitable distribution of resources.
Okay, that's definitely a good chunk of the goal. Yes?
I mean, you want to distribute the money such that every group gets as close to what they need as possible, given the constraints.
Be very careful about what you need.
Okay,
Because what if one school needs more, but historically, would you then say that Williamstown should send a couple of $100,000 to Lanesboro, or Lanesboro should send a couple of $100,000 to Williamstown because the need is greater?
Okay, that's true.
So I think the original formulation.
Then you have this other problem to define under the definition of need for some balance between historical distribution and forecasted.
Well, as soon as you start going to need, now you're in the situation where one town could have a cost to regionalize. So as soon as you put in need, so for instance, in the discussion right now, one of the things that's fixed is no town will lose their elementary school without their permission. You cannot have one town vote to close another elementary school. This has just happened in the Adams-Cheshire School District. Their school committee was 7 people, 4 from Adams, 3 from Cheshire. After lengthy discussions, the 4 members from Adams voted to close the elementary school in Cheshire. The 3 school committee members from Cheshire voted to keep it open. Motion passes 4-3. I am not going to say whether or not that was the right decision or the wrong decision. It's very bad that the decision ended up looking, all the people in one town are voting to close the school in the other town. It doesn't look good. They then go to pass the budget, but they don't have enough votes to pass the budget. And so all the people in Cheshire then vote against the budget. And so it was a mess. The school has been closed. They finally passed a budget. They're doing various things. But it was a real mess. And so there's a second part to it. The first part of the goal is we want to divide the money equitably.
So maybe the second part of the goal is, maybe you define it, the money is the change in the money given across the summation. So say if previously they were getting a total of $3 million,
right?
Then you maintain the original distribution, and then you fairly distribute the remaining $500,000 extra to those 3 districts on top of what they were already getting.
But if you keep the original baseline distributed the same, and then the new baseline change, you split in some way, you could still have a cost to a town to regionalize, And the other thing is you could have changing dynamics in a town that make it more eligible for state aid. So for instance, the state aid depends in part about how economically depressed you are. So imagine, say, the Lanesboro Mall cancels, imagine there's huge hardships, and all of a sudden their assessments go down enormously. Then they would end up getting more state aid, and then they should be getting that, not Williamstown Elementary.
Sure.
So whatever formula you have, you need to be able to predict how it should be assigned. So a big part of it is you want to distribute as close to the current. The state has the three numbers, they just don't share. You want to distribute according to those three numbers. The other part, and this is the subtler one that I really want to dwell on, because this is the difference between pure math and applying math, is you want people to believe it's equitable. It's not enough to be equitable. It is a little bit painful. It's only game one, but right now the New England Patriots are the worst team in the NFL. The only advantage is, no, there's actually no, the only advantage is they have a little extra time to prepare for the next game. All right. How many of you know the quarterback formula for football? All right, there's a formula to rate quarterbacks. Or in baseball, there's the wins above replacement. You have these very complicated formulas. It's not necessary to understand all the nuts and bolts that are used in it. You know, people are willing to just accept, okay, if you score 100 on the quarterback formula, you're doing really well. But there are times when you need people to understand what you're doing. You know, if you're making a pitch to your boss, you know, 2 or 3 levels above you, your boss's boss, your boss's boss's boss, something like that. They may not know as much math or stats as you do, and you have to convince them that you're right. If you have something that you're sending to the voters, you need to be able to convince the voters that it's right. And it has to look fair. So I would love to use maybe 40 different variables. Do we really need 40 different variables, and do we want to go through explaining that? We recently adjusted the regional agreement for capital building projects such as the high school building project. And we basically just used student population and essentially, you know, assessment values of properties in the towns. It's a fairly simple formula. The components are natural components. It seems fair. The other thing is, you know, we were talking about, you know, 0th order, 1st order, 2nd order effects. For a lot of these things, the difference is negligible. These extra variables provide very little additional predictive power. And you want to get a sense of how accurately do you need to solve the problem. You know, do I need to solve this to 4 digits of accuracy or 2 digits of accuracy? One of my favorite quotes about how accurate quantum mechanics is that the measurements are so precise, it's equivalent to measuring the distance between Los Angeles and Boston to within the thickness of a human hair. And to some extent, I don't even care if it's going this way or that way. Either way, it's impressive. Do we need to have 10 digits accuracy? If so, we might as well go home. You know, we're not going to get 10 digits accuracy in a simple formula. But what if we only need 2 or 3 digits accuracy? That might not be so bad, and that might be attainable. And so these are some of the issues that arise when you try to apply the mathematics. So right now, this is actually my assignment. My assignment was to figure out how to assign this $3.5 million between the 2 towns. And I was one of the people who was figuring out how to assign the capital building costs in the past. It was natural to do this. A lot of people do not know regression. And this is a problem that screams, well, let's do a linear regression, let's see how it works. All right, so the objectives, as I said, your fair formula that predicts well. You want to be transparent. You want to be able to tell people what you're doing and why. You don't want to have things in a black box that are hidden. And it's got to be something that you can explain. All right, so here's the solution. The method of least squares linear regression. So most of you have said you've seen regression before. And you know, I'll post a handout on how you do it. This is one of the reasons why we measure errors with squares rather than absolute values. Absolute values, calculus is not applicable. The absolute value function is not differentiable. The squared function is. And so when you use squared errors, you have an explicit solution. So if I want to write, you know, my, you know, X is my data matrix, beta is the, you know, combinations, and then Y is the output, the best value of beta that minimizes the difference between the observations and the predictions is given by this nice formula. So this is linear regression. And for a lot of problems, this is all you need to do to have a massive improvement. It's wonderful. It's explicit. It's entirely transparent. You give me the data. I don't have any decisions to make. I don't have to justify why I chose to look at it this way or that way. The only decisions you have are the variables you use. And so the variables we're using is the populations, essentially, of the 3 towns, schools. It's not as simple as the population because not all students are counted equally. There are in-town students, out-of-town students. We're not going to get into that. We'll just say population of the buildings. And we'll just say the property values of the towns. So those will be our 5 parameters. We also have the constant 1. So basically, you give me the numbers 1, the population of Lanesboro Elementary, Williamstown Elementary, Mount Greylock, the property assessment of Lanesboro, the property assessment of Williamstown. I have 6 quantities. And I will get some linear combination of that, and that will give me what % of the aid goes to Lanesboro, what % of the aid goes to Williamstown Elementary, what % of the aid goes to Mount Greylock. So there are 3 different regression problems to solve. I'll have 3 different sets of betas. I'll have 3 different sets of y, but I'll actually have the same matrix x. X is just the data matrix. Well, the population of Lanesboro doesn't change if I'm viewing it as a regression for the Lanesboro percentage or as a regression for the Williamstown percentage. So what's nice is this part here is constant. All that changes is the y. Okay, so I'm going to try to move because one of my feet has fallen asleep. Hope no one else has had anything fall asleep yet. What properties do you want the solution to have? So I'm going to get 3 numbers. I'm solving 3 regression problems, for the % of the money that goes to Lanesboro, to Williamstown, to the high school. It's actually the middle school, high school, but we always say high school. We screw the middle school students. I don't know. What do you want your solution to have? What properties?
Well, it should be between 0 and 1.
It should be between 0 and 1. Yes? It would be very bad if Williamstown Elementary gets negative 5.4% of the state aid. Okay, good. So we want the numbers to be between 0 and 1. What else?
Add up to 1 or close to it.
Add up to 1 or close to it. Well, if it adds up to something close to 1, what do you do with the extra money? Or what do you do if it adds up to something more than 1?
If it's more than 1, then you have to figure out how to subtract it from the different schools. But if it's less than, then you can probably just distribute it equally as a small amount.
So depending on how small the amount is, you could try to just distribute it equally. Another thing you could do is you could renormalize. Let's say it adds up to 1.5. Or then what you do is you take the Lanesboro amount and divide it by 1.5, the Williamstown by 1.5, and the Mount Greylock by 1.5. So you could actually always normalize. Any other properties you want the solution to have? There's a more basic one which you have not mentioned yet. It's so obvious it's sometimes hard to remember that you have to explicitly state it. What's a nice property for a solution to have? Good. What do you mean? What do you mean by real?
Not negative.
Well, in some sense, we already had that because you said you wanted between 0 and 1. We want it to exist. Right? It's really nice if the method gives you an answer.
This is an analysis class.
I'm sorry?
This is an analysis class.
This is an analysis class. The first thing you ask is, does the solution exist? What's your second question?
Is it non-negative?
I don't think that would be my second question. First question is, does the solution exist? Is it unique? Right? So the first question is, do I have a solution? Do I have more than one solution? What can I say about the structure of the solution? But the very first question is, does it exist? Well, when you look at this, is there anything that scares you in that expression? The inverse, right? If it wasn't for the inverse, if I just got rid of the inverse, the solution would exist. So my question is, will you always have a solution? So I tried to write down what I thought the questions would be. We want the solution to exist. We want the values to be between 0 and 1. The last one, which we didn't discuss, is we want the values to be stable under small changes. I don't want a butterfly effect, where if one more person goes to Williamstown Elementary out of 400, all of a sudden the percentages massively change. I want a solution that's stable. That seems reasonable. The other thing is, if the solution is not stable under small perturbations, then boy, we're going to have to measure everything accurately. I don't want to have the assessments be that precise. And then we want the sum of the three percentages to add up to 1. So your homework for Friday is to address these 4 questions. So, can you show that the percentages will add up to 1? I will let you know, yes, you can. I'm talking with Professor Klingenberg to see if anybody has ever explicitly remarked that this is a result. One of the things that's nice about this is as we're deriving the formula for the regional agreement, we don't have to worry about if the percentage of the 3 schools adds up to something less than 1 or more than 1, we renormalize. We're not going to have to worry about renormalizing. We will not include a math proof in the regional agreement. That will be supplementary white papers. Will the values always be between 0 and 1? What if it's not the case that they're always between 0 and 1? What if for some values of the inputs you actually have either a negative percent, and if there's a negative percent, what do you know must be true? So let's say one school, let's say Williamstown Elementary gets negative 5%.
Input variables, like real numbers, like population and like poverty values,
Mm-hmm.
all your coefficients are positive, you can't get a negative.
But you have an inverse.
But you have an inverse. You have x transpose x inverse. So there is the possibility. And then what you can do is, as an exercise, is try to come up with some numbers and see, is it possible to have a situation where you would have a negative percentage? And if one school has a negative percentage, then the other 2 schools have to add up to more than 100%. The money's going somewhere. So I'm going to leave that as something for you to consider. Do we need to put language in the agreement about what happens if a school is hit with a negative percentage? And then what will that look like to have language like that in the agreement? So the final document is not due until October 23rd. So there is time to have input from what you say in the regional agreement between the 2 towns. So this is a chance for you guys to apply math immediately in the real world. So here is a plot of what I got using linear regression, using data from 2007 to 2017, and then trying to predict what 2018 should be. So I have to figure out how to assign about $3.5 million to the 3 schools. What's nice is, since both towns already share the middle high school, if I give one town too much for their elementary school, the high school can actually pick up some of that because you get some money back from the difficulty there is split. So you can see the regression does a pretty good job. You're, for the most part, within 1%, a lot of time much less than 1%. So here are the numbers, the predicted, actual, and then the difference. So for Williamstown Elementary, we predicted it should be about 27.839. It was 27.876%. So the difference was about 0.03%. The other 2 schools were about 0.3%. To put things in perspective, and yes, they sum to 100, there was $3.489 million in 2018. 1% is $34,000. 0.3% is about $10,000. So we were giving predicted Lanesboro Elementary just a little bit less, Williamstown minuscule less, and the high school more. But since the high school gets more, both towns pay for the high school. So even though Lanesboro got a little bit less than they should have for the elementary school, they then got more for the high school. So it doesn't perfectly even out. But the cost to the town is not as bad as it might appear. So we're talking about errors in assignments on the order of $10,000 by just doing the linear regression. These are the skills you have right now leaving Williams. the amount of money we're getting in transportation savings to the districts from the state is on the order of $100,000 or $200,000. So this answers the question of how accurately do we have to be? If I'm within 1% of these numbers, so I've just got to be within 1% of those numbers, and then no town is hurt by the regionalization monetarily. You may not get the proper benefits. You may not benefit as much as you should have, but no one is put in a worse situation. People with economics classes here? What kind of equilibrium? I'm sorry? Pareto efficiency. So I was giving a presentation on this to the Williamstown Elementary School Committee, and one of the committee members said, so we're looking for Pareto optimal. And it's just so nice to be able to have a discussion like this. And he said he was thrilled afterwards that he was able to use the word Pareto in a school committee meeting. All right. The next one is hedging bets. Any baseball fans here? Anybody know what's going on with the Cleveland Indians? With the 15-game win streak. Yes. Yes. Did they win last night? They were up 10-2 in the ninth. Okay. Okay. So I just posted something from ESPN. The owner of a store that has been in business for about 15 years in Cleveland thought it would be fun to celebrate 15 years in business by saying, if the Indians win 15 games in a row anytime this season, all purchases in July are free. And so he took out an insurance policy on this. And so he spent $70,000 or $75,000, and it covered $1.7 million in sales. And so there was a nice article. There's been some articles on this as the Indian win streak has been getting closer and closer and closer to 15. I didn't even bother checking because they were up 10-2, I think, in the ninth inning. I was pretty sure Cleveland could hold. Yeah. And so all of the people who bought stuff in July, it's now free. I know Jordan's Furniture in Massachusetts had stuff like this when the Red Sox, the Red Sox will win the World Series in 4 straight games. If they do, all the stuff is free. And a lot of people got free furniture from Jordan, I think in 2004 and 2007. So here's my question to you. Is this a good price? Now, given that the Indians have just won 15 in a row, this is not a hard question to answer. Right? Was this a good price for the owner of the business? Yes. Was it a good price for the owner of the insurance company? No. So once the event has happened, we're no longer talking about insurance. Okay? So a lot of people misuse the word insurance. Right? Insurance is before the event happens. So now let's go back in time. Let's go to the start of the season. Do you think that this is a reasonable amount of money to ask? $75,000. So I don't want to talk too much about this right now. I want you to think how. I'm sorry.
You can explicitly.
Well, I don't.
If you estimate.
Well, okay. I don't want to go into too much right now, right? I want to let you all have some. Right. I want you to try to figure out how would you estimate how much you should charge for this. There's a great quote: "Someone must pay for Mr. Smith's suits." When someone is offering you insurance, is the insurance company expecting to make money or lose money on the deal? Make money. Why do you think they? Well,
Market making.
so every now and then you might be willing to lose money on something just to get people working with you and then get them on something else. For the most part, you prefer not to. But they have like Walmart will often have sale items that they sell at a loss because they want to get people in the store, and once in the store they'll buy other things. So you don't need to win every time, but you need to win more times than you lose. And sometimes you are willing to take losses. Read a wonderful article years ago about sport gambling, where if you are known to be phenomenal at predicting who wins games, and you go to Vegas and you want to bet money on a game, what happens? They don't take your money. Right. We don't want to play with you. We have the right not to enter into a bet. So what certain people do is they have people whose job it is to place bets for them. And so there's one person who was extremely successful who had a bunch of people. They were given instructions, and they were told, "Thou shalt do nothing but what I tell thee to do. You will put this money down on this team at this time. As long as you do this, I will pay you a good salary." And what this person would sometimes do is he would have people put down money for a team to win that he thought would lose. And he would have them put down maybe $40,000 on a team, and the whole point of this was to shift the line. And then once the line shifted, then he would have someone else put down $400,000 with a now slightly more favorable line.
How do you feel about the market making of the Mayweather-McGregor fight odds? Did you keep an eye on that?
No, I have not been keeping.
So the fight opened, I want to say Mayweather was like probably plus like 1,000.
Okay, so Mayweather, I'm just because I'm not sure this is going to be picked up. So Mayweather was plus 1,000 in the fight.
And so many people put down money on McGregor at like minus like some or whatever plus or minus some ghastly number, like some ghastly odds.
Right.
20 to 1. That it ended up being Mayweather closed around 1 to 4.
Wow.
And McGregor closed around like 5.5 to 1. It was like incredible swing with people running on the underdog.
Well, when Vegas sets the lines on sports, they're not setting their line on what they think will happen in the game. They're trying to equalize the money on both sides so that their risk is minimized. They want to take the money from Peter and give it to Paul while pocketing a small percentage for themselves. So when they say, we think this team by 7, they don't necessarily think the team by 7. They say, if we do that, we think half the public will we think half the money will be on them to win and half the money will be on them to lose. So the question here is, can you theoretically predict what the answer should be? And if you can't theoretically predict, what else could you do? So these are a little bit open-ended questions right now, but I want you to get thinking a little bit more freely. Here's a general problem. How do you want to phrase it? What are the key features? What do you want the solution to get? If you can't solve it exactly, can you approximate the solution? And for a lot of these things, is an approximate solution close enough? How close do we need to be? So for something like this, I don't think it really matters the number of hundreds over here. The real part is maybe going to within 1,000 or maybe even within $5,000. That's what really matters. We don't need to figure out the insurance plan to within 10 cents. And for those of you who took operations research, this is a lot of what we were doing with linear programming. We don't have to solve the problem exactly. We just need to be close enough to the answer that we're fine. Okay, so I think this is a pretty good place to stop. What we will do on Monday's class is we will start the theory lectures by doing, I think it's chapter 11 of the book, which is Fourier analysis. So how many of you have seen Fourier analysis before? Have you seen convergence of sums of sines and cosines to functions? Have you seen proofs of these? Okay, so nobody is basically screaming, oh yeah, we've seen lots of proofs as to why this linear combination converges to the initial function. So the big idea of calculus is you take a complicated function and you linearize it. Right, at this point, the slides no longer matter, so we can at least get some steps in for today. It's a shame I can't transfer the steps. I had 30,000 steps from walking, over 8 miles in New York City yesterday that don't carry over to today's. But the big idea in calculus is you replace a complicated function with a simple linear one. Close enough. So we were talking about being close enough. This is an example. So if I give you a complicated function, locally, any complicated function can be well approximated by a straight line. If you want to do a better job, this is the Taylor series, then you do the best fit parabola, then best fit cubic. And if you define appropriately what you mean by best fit, it should never get worse the more terms you take. Because a line is a special case of a parabola. A parabola is a special case of a cubic. How many of you have seen Newton's method? I think we did this in operations research. Have you seen Newton's method? So if you want to try to approximate where a function vanishes, what you do is you calculate the tangent line and see where the tangent line hits. And that becomes your next approximation. Then you go back to the curve and see, well, okay, it didn't actually hit I'm really this high, and now I'll take the tangent line there and see where it hits, and just lather, rinse, repeat. It converges exponentially fast. So now I'll put some notes on that if you haven't seen before. This was the set of homework problems that I saw my sophomore year that pushed me to math over physics. I was just floored by how well and how quickly this works. It's absolutely incredible. This is just the power of linearizing. So what's going on with Fourier series and Fourier analysis is rather than just looking at exponentials, we're trying to write a Taylor series. We're using 1x, x squared, x cubed. This was lower a moment ago?
Yeah, it
started moving up. Okay, that's what just making sure. And does anybody else hear the voices, or is it just me? Okay. So Taylor series is using the functions 1x, x squared, x cubed, etc. There are other choices of functions you can use. And Fourier analysis is using the functions e to the I theta, or more likely often e to the 2 pi I n x. We'll often do it like that, where n ranges over positive and negative and integers and 0. Or you can expand this, e to the I theta is cosine theta plus I sine theta, where I is the square root of negative 1. So has everyone seen this formula? Have you seen it? Okay. And so what we can do with this is rather than using this set of functions to expand, we use this set of functions. And it turns out this set of functions has a lot of really nice properties. It doesn't have as many nice properties as you would hope, and the Fourier series, just like the Taylor series, doesn't always converge to the function. So then the question becomes, well, when does the Fourier series converge? How quickly does it converge? How well does it converge? If it doesn't converge, does it have a close cousin who converges? And so we'll start talking about that in Chapter 11. We'll go through the basics, and we'll prove some of the fundamental convergence results. We will not prove the most general types of convergence you get. I'll just let you be aware of them, but I'll concentrate more on the standard convergence of if your function is nice, what happens. And as a rule of thumb, the nicer your function is, the better convergence you have. And the way we measure how nice a function is how often we can differentiate it. So the more you can differentiate it, the nicer it is, the better convergence you get. Okay, so this is a good time to stop. Okay, good. It is somewhat